Okay, so if all the proofs I'm plastering it as example 1, starting with example 2 here, and how we then apply them. So I'm going to look, this is all non-calculator, don't forget at the moment, try and find the exact value of sine 105 degrees. And I use the fact I'm using standard angles, so I want to use sort of 30, 45, 60s and 90s. Now I know that 105 is 90 at 15, but 15 is not a standard angle. So I'm going to treat it as sine of 60 plus 45. I split it up. So sine 60 cos 45 plus cos 60 sine 45. And now it's knowing that sine 60 is root 3 over 2, cos 45 1 over root 2, and cos 60 the same as sine 30 is half as 1 over root 2. And then I end up with root 3 plus 1 over 2 root 2, or times everything by root 2 to get root 6 plus root 2 all over 4. And that is the exact value of sine 105. A couple of other ones here to actually just simplify and maybe do something with, depending. I've got sine 50 cos 10 minus cos 50 sine 10. Well, that's sine of a difference. That's sine 50 minus 10, which is sine 40. And I can't do a great deal with that apart from leaving it as sine 40. Similarly, cos plus sine is cos of a difference. So it's cos of 7x minus 2x, which is cos 5x. Yet again, that's all I can do with it. We then potentially use it on something else later on. Here's a nice example here. I've got tan of a sum, tan x plus y equals 1, and tan x is a half. I'd be surprised if tan y is a half, but we're going to find the value of tan y from this. So, I do my expansion of tan of x plus y. There's tan x plus tan y over 1 minus tan x tan y. I'm doing my substitutions, a half plus tan y equals 1 minus a half tan y. And that put it equal to 1 because that's what we're told in the question. A bit of cross multiplying, 1 minus a half tan y equals a half plus tan y, great stuff. And then move things across, and I get 1 minus a half equals 1 plus a half, 3 over 2 tan y. Tan y is that over that, which is 1 over 3, third. And that's our exact value, and that's all I have to do. Next example, solving an equation. So example 5, solve sine of x plus 30 equals 2 cos x, x is in the range 0 to 360. So, do my expansion, sine x cos 30 plus cos x sine 30 equals 2 cos x. Put my values in, cos 30, root 3 over 2, sine 30, a half times cos x equals 2 cos x, times by 2 because I don't like fractions, root 3 sine x plus cos x equals 4 cos x. And then, because I've got sine and cos in, I want everything with cos on one side, everything with sine on the other, and probably form a fraction in tan. So I get root 3 sine x equals 3 cos x, and cross multiply, cross divide, tan x, which is sine over cos, equals 3 over root 3, which is root 3. And that's nice because I was panicking then, I haven't got my calculator, but I know that tan 60 is root 3, and tan repeats every 180, so 60 and 240 are my two solutions in 0 to 360.
1.
Okay, and the last example is we're going to be asked to find an exact expression for a particular fraction, the right one, cos of a plus b, when we're given these values for cos a and sine b. We do not have to find the angles A and B. This is all, in theory, non-calculator based. A bit of calculation to find the things here. So, cos A, we treat it says it's acute, but we're going to treat everything as being acute initially, and from that we're going to find the exact values of sine, cos and tan if we need them. So there's angle A. Cos A, adjacent, 20, over hypotenuse, 29, which means by Pythagoras, the opposite side, 21. It's a Pythagorean triple. They generally tend to use Pythagorean triples quite a lot in these. So I can say that sine A then, as I need it, is opposite over hypotenuse, 21 over 29. Sine B, opposite, over hypotenuse 25, by Pythagoras, the adjacent side is 24. Which means that in this triangle, cos B, adjacent over hypotenuse, will be 24 over 25. There's a but. We are told that B is obtuse. Now if it's not in the 0 to 90 range, then only one of the three trig things is positive and the other two are negative. And because obtuse, 90 to 180, it's telling us that sine is positive anyway, which we know, but it's telling what it means is that the cos value here has to be a negative value. So our method, treat the angles as if initially they are acute in part of a right angle triangle, and if they're not, then you've got to use your cast diagrams or whatever your method is to write the actual plus minus that goes with it. The values, the size of cos B will be that. But because it's an obtuse angle, it has to be negative, so it's minus 24 over 25. I've now got the four values I need to find, done it again, cos of the sum. And it's always good practice to quote the formula you're going to use, especially since you're given it in the formula book. I've seen people quote it incorrectly. They don't get many marks in that case there. So it's cos minus sine, cos of a sum. So cos A, where's cos A? 20 over 29. Times cos B minus 24 over 25, and then minus sine A, 21 over 29, times 7 over 25. I could do some cancelling here and here, but it does mean that it's going to be awkward in terms of putting the fractions together. I might as well leave them over the same denominator. And I've got 29 times 25 is going to test my mathematics, I think 725, and I've got minus 480 minus 147, and it gives me minus 627 over 725. If you have time, obviously, you can use calculators and find the actual angles themselves, and remembering that B should be obtuse, add them together, and then realise you're going to get probably a reflex angle, and it's no surprise then, if it's between 180 and 270, you're going to get a negative value for the cos of the sum angle. And that's our method. As I say, when we're given the exact values, at no stage, I might have needed a calculator to find the values of the 21, to find these numbers here, but I'm not finding the actual angle A, the actual angle B.